Right now, the furthest humans have ever traveled from Earth is 248,655 miles. That was the Apollo 13 crew in 1970. In cosmic terms, that's basically nothing. We haven't even left our planetary neighborhood. But if we actually tried to go as far as physically possible within a human lifetime, where would that limit be? The answer involves physics, biology, and some deeply uncomfortable truths about the universe's size. Before we can understand how far humans can travel, we need to understand the fundamental barrier that limits all travel in the universe: the speed of light. Light travels at 186,282 miles per second, or about 671 million miles per hour. This seems unimaginably fast by human standards. At light speed, you could circle Earth's equator 7.5 times in 1 second. You could reach the moon in 1.3 seconds and the sun in 8 minutes. But space is incomprehensibly vast. Even at light speed, reaching our nearest neighboring star system, Alpha Centauri, takes 4.2 years. The center of our galaxy is 26,000 light-years away. The nearest large galaxy, Andromeda, is 2.5 million light-years distant. According to Einstein's special theory of relativity, nothing with mass can reach or exceed the speed of light. As objects approach light speed, their mass effectively increases, requiring exponentially more energy to accelerate further. Reaching exactly light speed would require infinite energy, which is impossible. This isn't a technological limitation we might overcome with better engineering. It's a fundamental law of physics, as certain as gravity. The speed of light is the universe's ultimate speed limit. For human space travel, this creates a harsh reality. Even if we could somehow build a spacecraft capable of traveling at 99% light speed, an extraordinary engineering achievement requiring physics we don't yet possess, the distances between stars would still take years or decades to cross. Our fastest spacecraft to date, the Parker Solar Probe, reaches about 430,000 miles per hour at its closest approach to the Sunday. That's 0.064% the speed of light. At that speed, reaching Alpha Centauri would take roughly 6,700 years. The entire recorded history of human civilization is only about 5,000 years long. To travel meaningful distances in space within a human lifetime, we need to go much, much faster. But how fast can we realistically go? Let's start with what we can actually do right now with existing technology and near-future developments. Chemical rockets, the kind that launched the Apollo missions and currently send satellites and astronauts to orbit, are limited by their fuel's energy density. The best chemical reactions produce exhaust velocities around 4.5 kilometers per second. This fundamentally limits how fast they can accelerate payloads. The rocket equation, derived in the early 20th century, shows that achieving higher speeds requires exponentially more fuel. To go twice as fast, you don't need twice as much fuel. You need exponentially more. Eventually, the spacecraft becomes almost entirely fuel with barely any room for payload. Using chemical rockets alone, the maximum practical speed for interplanetary travel is roughly 50 to 70 kilometers per second, which is what New Horizons achieved using gravity assists from Jupiter. At that speed, you could reach Mars in a few months and the outer planets in several years. But leaving the solar system takes much longer. Voyager 1, launched in 1977 and still traveling, is currently about 15 billion miles from Earth, moving at 38,000 miles per hour. It took over 45 years to reach interstellar space, and it would take another 75,000 years to reach the distance of Alpha Centauri if it were headed in that direction, which it's not. Ion drives offer better efficiency. These engines use electricity to accelerate ions to extremely high speeds, producing tiny but continuous thrust. NASA's Dawn spacecraft used ion propulsion to visit asteroids Vesta and Ceres, achieving velocity changes impossible with chemical rockets of the same mass. However, ion drives still face limitations. They need electrical power, typically from solar panels or nuclear reactors. They produce very low thrust, taking months or years to reach high speeds. And they still can't approach relativistic velocities, speeds that are significant fractions of light speed. nuclear propulsion offers more promise. Project Orion, proposed in the 1950s, envisioned using nuclear bomb explosions for propulsion. Small nuclear devices would detonate behind a massive shock absorber, pushing the spacecraft forward. Calculations suggested this could achieve 3 to 5% of light speed. At 5% light speed, Alpha Centauri becomes reachable in about 85 years. That's a single human lifetime, albeit a very long one. But Project Orion was never built due to nuclear weapons treaties, technical challenges, and the environmental consequences of launching nuclear devices from Earth. More advanced concepts like nuclear fusion propulsion could theoretically reach 10% light speed. This would reduce the trip to Alpha Centauri to roughly 42 years. Still a lifetime, but potentially viable for a dedicated mission. These represent the upper limits of foreseeable propulsion technology that doesn't require revolutionary new physics. With nuclear propulsion, humans could potentially reach nearby star systems within a single lifetime. But we're talking about the closest stars, just a few light years away. The vast majority of our galaxy remains unreachable with these technologies. The Milky Way is 100,000 light years across. Even at 10% light speed, crossing the galaxy would take 1,000,000 years. Even if we solve the propulsion problem, human biology creates severe constraints on long-duration spaceflight. Radiation is the first major issue. Earth's magnetic field and atmosphere protect us from cosmic radiation and solar particle events. In deep space, astronauts receive continuous exposure to high-energy particles that damage DNA and increase cancer risk. The Apollo astronauts spent only days in deep space beyond Earth's magnetic field. Mars missions would require months or years of radiation exposure. Interstellar missions, lasting decades, would accumulate radiation doses far exceeding current safety limits. Shielding helps, but requires mass. Water, hydrogen-rich materials, and thick metal all block radiation effectively, but adding several feet of shielding around a spacecraft increases mass enormously, requiring more fuel, which requires more mass, creating a difficult design spiral. Active shielding using magnetic fields has been proposed, but would require enormous electrical power and complex engineering to create fields strong enough to deflect cosmic rays. Microgravity poses another challenge. Extended weightlessness causes bone density loss, muscle atrophy, fluid shifts, and vision problems. Astronauts on the International Space Station exercise 2 hours daily just to maintain minimal fitness. For journeys lasting years or decades, microgravity's effects would be devastating without countermeasures. The human body simply isn't designed for weightlessness over long periods. Rotating spacecraft could create artificial gravity through centripetal force, but this requires large structures and introduces engineering complications. The rotation must be carefully controlled to avoid disorienting effects, and any mechanical failures could be catastrophic. Psychological factors matter too. Isolation, confinement, and separation from Earth create mental health challenges. Antarctic research stations and submarine missions provide some insight, but nothing matches the complete isolation of interstellar travel. A mission to Alpha Centauri taking 40+ years means astronauts would spend their entire adult lives aboard a spacecraft. They'd never feel wind, rain, or walk on solid ground. Many would die before arrival. The psychological toll might prove unbearable. Then there's the resource question. Humans need air, water, food, and waste recycling for decades. Creating truly closed-loop life support systems that function perfectly for 40+ years is extraordinarily challenging. Any failure could be fatal. These biological and psychological barriers suggest that very long-duration missions may need to be generational. Instead of one crew making the entire journey, multiple generations would live and die aboard the spacecraft, with descendants completing the mission. Generation ships introduce additional complications. You need enough people to maintain genetic diversity and avoid inbreeding. Estimates suggest a minimum of 500 to 1,000 people. That's no longer a spacecraft. It's a small town in space, requiring enormous resources. Children born on a generation ship face ethical questions. They never chose this mission. They're committed to life aboard a spacecraft by their parents' decisions. Is this morally acceptable? If we could somehow overcome propulsion and biological barriers, reaching substantial fractions of light speed opens strange possibilities through Einstein's relativity. Time dilation means time passes differently for observers moving at different speeds. For someone traveling at high velocity, time passes normally from their perspective. But relative to stationary observers, their time slows down. This effect is negligible at everyday speeds, but becomes significant at relativistic velocities. At 90% light speed, time aboard your spacecraft runs at about 44% the rate of time on Earth. 1 year for you equals 2.3 years on Earth. At 99% light speed, time dilation is dramatic. 1 year for you equals about 7 years on Earth. At 99.9% light speed, 1 year for you equals roughly 22 years on Earth. This creates a remarkable possibility. From the traveler's perspective, you could cross vast distances in relatively short times through time dilation, even though you never exceed light speed. If you could maintain 99.9% light speed with continuous 1 gram acceleration and deceleration, you could reach the galactic center 26,000 light-years away in about 20 years of ship time. You'd arrive to find Earth 26,000 years in the future, but you would only age 20 years. In principle, you could travel anywhere in the observable universe within a human lifetime from your perspective, given sufficient acceleration. Want to reach Andromeda Galaxy, 2.5 million light-years away, with constant 1 gram acceleration and deceleration, you'd experience about 28 years of travel time. Of course, on Earth, 2.5 million years would pass. Everyone you knew would be dead for millennia. Human civilization might not exist anymore, but you'd arrive having aged less than 3 decades. This is the strange gift of time dilation. It allows for relativistic travel across the universe within a single human lifetime from the traveler's frame of reference. However, the energy requirements are astronomical, accelerating even a small spacecraft to 99.9% light speed requires energy equivalent to millions of nuclear bombs. Accelerating a crew-carrying vessel with life support, shielding, and supplies would require far more. There's no known energy source capable of this. Even perfect matter-antimatter annihilation, converting 100% of mass to energy, would require carrying tremendous amounts of fuel, and antimatter is difficult to produce and store. Some theoretical concepts, like the Bussard ramjet, propose collecting hydrogen from space and using it for fusion propulsion. But the technical challenges are immense, and it's unclear if such designs could actually achieve the required velocities. Given all these factors, what's the realistic maximum distance humans can travel in space within current or foreseeable technology? For missions using chemical or ion propulsion, the practical limit is our solar system. Mars is reachable in months, Jupiter and Saturn in years, the outer planets in a decade or more. But leaving the solar system entirely would take multiple human lifetimes. With nuclear pulse propulsion like Project Orion, achieving 3 to 5% light speed becomes theoretically possible. This puts nearby stars within reach in 50 to 100 years, which is a long human lifetime but potentially doable. At this speed, the practical limit expands to perhaps 10 to 20 light-years from Earth. This encompasses roughly 50 to 100 star systems, depending on stellar density in our galactic neighborhood. A human born on such a mission might arrive at the destination as an elderly person, having spent their entire life in transit. This requires either accepting one-way journeys, where the original crew never returns, or generation ships, where descendants complete the mission. With advanced fusion propulsion reaching 10% light speed, the limit extends to perhaps 30 to 50 light-years, encompassing several hundred star systems. Journey times drop to 30 to 50 years one way, making return journeys theoretically possible within a single extended lifetime. These distances represent a tiny fraction of our galaxy. The Milky Way contains 100 to 400 billion stars, spread across 100,000 light-years. At 10% light speed, you could explore perhaps 0.01% of the galaxy in a human lifetime. For relativistic travel at 50% plus light speed, which would require revolutionary breakthroughs in physics and engineering, the practical limit expands dramatically due to time dilation. From the traveler's perspective, significant portions of the galaxy become reachable within a lifetime. But this comes at the cost of complete disconnection from Earth. At these speeds, Time dilation means decades or centuries pass on Earth for every year of ship time. You could never return to the civilization you left. Communication would be impossible due to time delays. The absolute theoretical maximum, assuming physics we don't currently possess and energy sources beyond anything available, would allow travel to the observable universe's edges within a human lifetime from the traveler's perspective through extreme time dilation. But this is so far beyond current capabilities that it remains purely theoretical. The energy requirements, engineering challenges, and unanswered physics questions make it speculative at best. If physical travel faces such severe limits, what alternatives exist? Suspended animation or cryogenic preservation could allow humans to survive long journeys without aging. If we could safely freeze and revive people, journey duration becomes less critical from the passenger's perspective. However, we can't currently do this. Every attempt to cryogenically preserve and revive complex organisms has failed. Ice crystals, damaged cells, metabolic processes can't be restarted reliably. The technology remains science fiction. Even if perfected, it doesn't solve propulsion or energy problems. The spacecraft still needs to travel at reasonable speeds, still needs power for life support systems to maintain frozen passengers, and still needs to function perfectly for decades or centuries. Generation ships, where multiple generations live and die during the journey, represent another approach. This is technically feasible with current knowledge, though never attempted. The challenges are social and ethical rather than purely technical. Creating a stable society in a confined space for generations requires careful planning. Education, culture, purpose, all must be maintained across generations who never chose this life. Digital consciousness or uploaded minds represent more speculative possibilities. If human consciousness could be digitized and transmitted as data, we could theoretically send information to distant star systems at light speed, reconstructing people at the destination. This requires technology and understanding of consciousness we don't possess. The philosophical questions are profound. Would a digitally reconstructed version of you actually be you, or just a copy? Self-replicating probes offer a non-human alternative. Send robotic probes to nearby stars. Have them build copies of themselves using local materials. Those copies travel to more distant stars and repeat. This exponential expansion could explore the galaxy relatively quickly without requiring human presence. The probes could terraform planets, preparing them for eventual human colonization, or simply gather information and transmit it back. However, this doesn't solve the problem of actually getting humans to those locations. It just provides information and potentially prepares destinations. Stepping back from technical details, the limits on human space travel reveal something profound about our place in the universe. The observable universe is roughly 93 billion light-years across. It contains an estimated 2 trillion galaxies, each with hundreds of billions of stars. The sheer scale is incomprehensible. Yet even with revolutionary propulsion advances, humans could realistically explore only a tiny bubble around Earth, perhaps 50 to 100 light-years across. That's 0.0001% of our galaxy, and an infinitesimally small fraction of the universe. The vast majority of the cosmos is forever beyond human reach. We can observe it through telescopes. We can study it through physics and mathematics, but we will never physically visit it. This is a sobering realization. The universe is filled with wonders we'll never touch. Trillions of planets orbiting distant stars, galaxies colliding and forming, black holes consuming matter, all happening at distances we cannot cross. Some find this depressing. We're confined to one tiny corner of existence, unable to explore the vast cosmic ocean around us. Our species, for all its achievements, is fundamentally limited by physics itself. Others find it humbling and oddly comforting. It reminds us that we're not the center of existence. The universe existed for billions of years before us and will continue for trillions more after we're gone. Our limitations are part of the natural order. It also emphasizes the preciousness of Earth and our solar system. This is our home, likely the only part of the universe we'll ever directly influence. What happens here matters because we can't simply move elsewhere if we damage our planet beyond repair. So how far can humans actually travel in space before it becomes impossible? With current technology, we're limited to our solar system, and even reaching the outer planets requires decades. With foreseeable advances in nuclear propulsion, we might reach nearby stars within human lifetimes, exploring a bubble perhaps 50 light-years across. With revolutionary breakthroughs requiring physics we don't yet understand, relativistic time dilation could theoretically allow travel across the galaxy or even to nearby galaxies within a human lifetime from the traveler's perspective, though Earth time would advance by thousands or millions of years. But the vast majority of the universe, hundreds of billions of galaxies spread across billions of light-years, remains forever beyond our physical reach. We are confined to one tiny region of space by the fundamental laws of physics. This is the humbling truth of space travel. The universe is magnificent and vast beyond comprehension, and we are small, limited, bound to one world and perhaps a few nearby stars. But that doesn't diminish the value of exploration. Every mission we undertake, every planet we visit, every star system we study, expands human knowledge and experience. We may never travel to distant galaxies, but we can understand them through science. And perhaps that's enough. To know the universe exists, to comprehend its structure and evolution, to wonder at its beauty even from a distance. To be conscious beings capable of contemplating the cosmos that created us. The practical limit on human space travel is severe, but the limit on human understanding and curiosity is boundless. What do you think? Should we accept these limits or keep pushing for breakthrough technologies? Share your thoughts below. And if you want more reality checks about space exploration, subscribe, because the universe is amazing, but it's also honest about the challenges we face in exploring it.